Hi there, I'm Juno, and I'm really excited you want to learn Python. Before coming to Udacity, I worked as a data scientist and used Python for data analysis, machine learning, and deep learning projects. Python is one of the most widely used programming languages in industry. It's a powerful, general-purpose language with applications ranging from web development to data science. In this course, you'll learn how to apply Python and good programming practices to solve practical problems. As you learn Python throughout this course, there are a few things you should keep in mind. First, unlike languages like SQL, Python is case-sensitive, meaning these two words mean two different things. Second, spacing is important in Python. Since it isn't very heavy on syntax, like other languages, it relies a lot on spacing, which can be confusing at first, but really nice and clean when you get the hang of it. Third, there will be times you get errors in this course. Keep in mind, errors don't make you a bad programmer. It's just a computer telling you it doesn't understand. Use error messages to help you learn how to write code that can be interpreted the way you wish. Let's get started.
When we go about using technology every single day, we don't realize that these programs are built by people who learned how to code. And if they can learn, so can anyone.
I have no background at all in programming, and I wanted to do it, but I never believed that I could. But now that I'm finishing up, now I'm kind of seeing myself professionally in that environment.
You can work alongside people who have tech skills, or you can become an engineer yourself. Honestly, the options are endless. So let's get started.
Welcome to this lesson on data types and operators. This is a very important lesson because it's where you'll learn about the building blocks of Python, data types and operators. Students tend to learn how to program at different rates. Take your time understanding each of the concepts that follow and getting practice with the activities in this lesson. Having a firm grasp on these building blocks will provide a strong foundation for future lessons and essential skills to continue programming beyond this course. Throughout this course, we'll go through code examples using these boxes. This first box represents the code editor, which is where we'll input our Python code. And the second box represents the output window, which is where our results will be displayed. You can follow along with the video examples in the classroom by typing in the code editor below each video. Click the Test Run button to run your code and view the results in the output window. You'll be seeing this print function pretty often. It helps us see what's going on in our code. For example, let's say you wanted to compute 3 plus 5. If we ran this line of code, Python would still add 3 and 5, but we wouldn't see the result because we didn't tell Python to do anything with it. Print is a useful built-in function in Python that we can use to display our results. All we have to do is type in print, followed by parentheses around whatever we want printed. You will be using print often as you get to know the building blocks of Python, its data types and operators. In the last video, you saw this line of Python that computes the sum of 3 and 5. The plus sign in this line is an arithmetic operator. Python has several arithmetic operators, most of which follow the usual rules of mathematics. Let's look at the first 4. In Python, addition and subtraction are performed with the usual symbols, plus and minus. Multiplication uses an asterisk, and division uses a /. Here, you can see that multiplication happens before addition. This is because Python follows mathematical order of operations, which you can get a refresher on in the notes below. If you want addition to come first, you can enclose this part in parentheses. Moving on from those 4, here's the operator for exponentiation. You can raise one number to the power of another with 2 asterisks. For example, this line prints 3 to the power of 2, which results in 9. There is another operator that is sometimes mistaken for the exponentiation operator, the caret. This actually performs a more obscure operation called bitwise XOR. This is an arithmetic operator that doesn't follow the usual rules of mathematics. Bitwise operators are not something you need to know for this course, but if you're interested, there's information about this in the notes below. All you need to remember is that if you perform exponentiation, you use 2 asterisks, and not with a caret, or you'll accidentally produce very confusing results. Another useful operator is this percent sign, which performs the modulo operation. It returns the remainder after you've divided the first number by the second. In this example, 9 divided by 2 is 4 with a remainder of 1. So this line would print 1, since modulo gives us the remainder. You might also find use for integer division, denoted by 2 forward slashes. It divides one integer by another, but rather than giving the exact answer, it rounds down the answer down to an integer. 7 divided by 2 is 3.5, which rounds down to 3. Notice it rounds down even if the answer is negative. In this case, negative 3.5 was rounded down to negative 4. There are other categories of operators that we'll learn about soon, but these are all of the arithmetic operators in Python. Understanding how to perform arithmetic in Python is useful, but understanding how to use variables can turn Python into more than just a calculator. Using variables, as opposed to just raw numbers, has many advantages. Let's get started. Creating a new variable in Python is simple. Here's one which stores the population of Mountain View. The variable name in this example is mvPopulation. The equal sign is the assignment operator, and the value of the variable is 74,728. Notice this isn't simply an expression of a quality, like in math, where x equals y and y equals x mean the same thing. In Python, the equal sign is an operator that assigns the value on the right to the variable name on the left. In other words, whatever term is on the left side is now a name for whatever value is on the right side. Let's see another example. The first line here defines x as 2, and the second line defines y as the value of x, which is printed in the third line. Notice we can use a variable's name to access its value. In this line, we only needed the name of the variable x to define y as its value, 2. Similarly, in this next line, we were able to print the value of y just by using the name y. If you try to access the value of a variable that was never defined, you'll get this error. It's explained pretty clearly in the error message. Name z was not defined. Python also has a useful way to assign multiple variables at once. These 3 assignments can be abbreviated using multiple assignment like this. X is still assigned to 2, y to 3, and z to 5. You can use this when you're assigning closely related variables like the width and height of an object, or an object's coordinates. In this example, we used x, y, and z as variable names. However, normally we'd want something more descriptive. X, y, and z would be appropriate variable names for something like coordinates in a 3D space. But for most other situations, we can do better. For example, if you were computing the population density of Mountain View by dividing the population by the land area, this is one way to compute the correct answer. But it's much clearer with these variable names, which are actually descriptive of the values they represent. In addition to being descriptive, there are a few things to watch out for when naming variables in Python. First, only use ordinary letters, numbers, or underscores in your variable names. They can't have spaces and need to start with a letter or underscore. Second, you can't use reserved words or built-in identifiers that have important purposes in Python, which you'll learn about throughout this course. They're also linked below. Using them as variable names will lead to errors or problematic situations when you try to use that word for its intended purpose. Third, the Pythonic way to name variables is to use all lowercase letters and underscores to separate words. We've already set MV population to this value, but what if we want to update it now that the population changed? We can just assign this variable again to its new value, which we found to be 78,128. Or if we got this new value because we knew 4,000 moved to Mountain View and 600 moved away, we could just apply those changes directly to this variable. In this line, the variable MV population is being assigned to itself plus 4,000 minus 600, which results in 78,128. Because this kind of increment and reassign operation is very common, Python actually has special assignment operators for this. Instead of using MV population twice in one line, we can actually use this plus equals operator to tell Python we are incrementing the variable on the left by the value on the right. Plus equals is one example of another assignment operator in Python. Minus equals is another. And there are a bunch more. These are actually just all of the arithmetic operators followed by an equal sign. All of these operators just apply the arithmetic operation to the variable on the left with the value on the right and makes your code more concise, which is good. Check out the text below this video for more assignment operators. So far, most of the numbers we've been working with have been whole numbers, or integers. However, as you may have noticed, other types of numbers do exist in Python. Here, dividing one integer by another gives us a number that isn't an integer, 0.75. In Python and computing in general, we represent such a number as a float, which is short for floating point number. A float is a real number that uses a decimal point to allow numbers with fractional values. Even if one integer divides another exactly, the result will be a float. The int and float are actually two kinds of data types. In Python, every object you encounter will have a type. An object's type defines which operators and functions will work on that object and how they work. You can check the type of any object directly using the built-in function type. Here, you can see that the type of a number without a decimal and a number with a decimal are different in Python. To make an int, just give a whole number without a decimal point. Here is an int. To make a float, include a decimal point. If the number itself is actually a whole number, that's okay. You don't even have to put anything after the decimal point. These are both floats. An operation involving an int and a float always produces a float. Sometimes you might need to manually convert one numeric type to another, and you can do that by constructing new objects of those types with int and float. When we convert a float to an int, the part of the number after the decimal point is cut off, which means that no rounding occurs. 49.7 is cut to 49. 4.0, calculated from 16 divided by 4, is cut to 4. Converting from int to float adds decimal 0 to the end of the number. So we've seen Python's two main numeric types, integers and floating point numbers. What are they good for? There are many times when you might need to count items or need to rely on the result of a computation being an integer. For example, let's say you want to count how many people showed up to your dinner party. You can't count 0.47 of a person, so you use an integer. If what you're working on isn't necessarily a whole number, a float is the type you're looking for. For example, let's say you made 5 pies for your dinner party and you want to keep track of the amount of pie left. People usually take 1/6 of a slice. Once one slice is taken, you're down to 4.83 pies. So you use a float. Floating point numbers are approximations of the numbers they're supposed to represent. This is necessary because floats can represent an enormous range of numbers. So in order to fit numbers in computer memory, Python must use approximations. This trade-off can sometimes have surprising results. Because the float, or approximation, for 0.1 is actually slightly more than 0.1, when we add several of them together, we can see the difference between the mathematically correct answer and the one that Python creates. In most contexts, these small differences are irrelevant, but it's important to know that they're there. You can read more about this in the instructor notes. One thing you might have noticed is that in a single line of Python, whitespace doesn't really affect how your code works. For example, this will give exactly the same output as this. However, that doesn't mean that these lines are equally good lines of code. Learning how to write clear and readable code is critical for others in your company and future you to understand. Here are some best practices for code style in Python. When you call a function like print, put the opening parentheses straight after the name of the function, like here. Not like this. Don't put extra spaces immediately inside the parentheses either. So this is good, but this isn't. If you are mixing operators with different priorities, like multiplication and subtraction, then you might like to add a space around the lower priority, in this case subtraction, to make the code easier to read. See how this is slightly harder to comprehend for operation order? Don't write extremely long lines of code. They're hard to understand. People commonly limit themselves to lines that are 79 or 99 characters long. If you feel like you need to write longer lines, consider rewriting, simplifying, or separating your code into multiple lines. These conventions come from the Python Developer's Guide, which has a style guide called PEP 8, which is linked below. There's a lot in there. Don't worry, you don't need to digest it all now. Why are these conventions important? Although how you format the code doesn't affect how it runs, following standard style guidelines makes code easier to read and consistent among different developers on a team. So it's a good idea to follow the guidelines even with one-line expressions. It will be useful to refer back to PEP 8 once in a while to get your Python style right. Later, we'll also learn about tools that can check your code for you and provide suggestions based on PEP 8 guidelines. We've seen two kinds of Python data types so far, ints and floats, and we've used arithmetic operators like addition and exponentiation to work with these values. Another type is bool, which is used to represent the values true and false. Bool is an abbreviation of Boolean. Boolean algebra is a branch of algebra dealing with variables whose values are true or false. Boolean algebra is named for its inventor, George Boole. Boolean logic underpins all digital devices, existing in almost every line of computer code, and has transformed the way we live our lives, which you can read more about in the instructor notes below. We can assign Boolean values like this. It's not very useful on its own, though. We can use comparison operators like less than and greater than to compare values and produce a Boolean result. Here, 42 is not greater than 43, so printing the result provides the Boolean false. Here, you can see a full list of the comparison operators in Python: less than, greater than, less than or equal to, greater than or equal to, and not equal to. Notice that evaluating equality is performed with two equal signs, and a not equal uses an exclamation point. This is a bit different than Excel or SQL. In addition to comparison operators, these logical operators are very useful when working with Booleans. And evaluates if both sides are true, or evaluates if at least one side is true, and not inverses a Boolean type. Here's an example that evaluates whether age is within the range of a teenager. Here, you can imagine the 14 being placed in these two spots. Then, if both are true, true will be assigned to the variable isTeen. In other words, if the person is older than 12 and younger than 20, this person is a teen. And here's not in action, inversing the Boolean type of this same statement. Often, programming involves more than numbers and arithmetic. There may be situations where you need to work with text. To work with text in Python, you will need to use a string, which is an immutable ordered series of characters. More on the immutable ordered part later. You can create a string by using quotes. Single or double quotes work equally well, although there are some edge cases which we will work through. In each of these cases, I printed the string hello and got the output hello. We can set a variable to be a string the same way we did with numbers. Strings can include any characters, even spaces, punctuation, and numbers. However, what do we do when we want quotation marks in our string? Since we use quotation marks to define our strings, this presents a small problem. Here, the code doesn't work the way we want it to. Python offers two solutions to this problem. The first is to place the string in single quotes rather than double quotes, like this. You can use either type of quote to define strings. But sometimes you'll need to define a string that includes both single and double quotes. What then? In that case, you can use a backslash to escape quotes. Here, the string is delimited by single quotes. The single quote within the string is preceded by a backslash so that Python knows that it should be interpreted as part of the string rather than the quote that ends the string. Once our strings are defined, there are a few operations that are used for integers and floats that we can also use for strings. For example, we can use the plus sign to put strings together, and we can use multiplication to repeat strings. Let's look at an example of each. Here, our variables are holding two words. We can use the plus sign to concatenate the two strings together and print the result. This is fundamentally different from numeric addition. However, notice the two names have been squished together. We're missing a space. Python is completely literal when working with strings. We need to explicitly include spaces and punctuation if we want what we write to make sense. This time, we got a string that makes sense, putting the two words together with a space in between. Note that previously, I said white space doesn't matter in between parentheses in bits of code like print statements. Here, with strings, you can see that spaces do matter in between the quotation marks. Let's try another mathematical operation. Turns out we can use the multiplication operator as well. It repeats the string as many times as you multiply it. Here, 5 times. Although addition and multiplication have different applications for strings, subtraction and division do not. Here, we get an error that a string is an unsupported type for the division operator. A useful function that's built into Python is len, which can tell us the length of a string. This is just the number of characters in the string. Len is like print in that it's a built-in function that takes in a value in parentheses to perform an action. Len differs from print in that it returns a value that can be stored in a variable. In this example, the len function outputs the number 7, which is stored in the Udacity length variable. Built in just means Python provides these functions for us. Later, we'll learn how to define our own functions. Up until now, we've discussed 4 data types in Python: int, float, bool, and string. If you recall from a previous video, you can check the type of any object directly using the built-in function type. Using type, we can observe that the same number can be coded in different types, each with their own set of behaviors. As a side note, here we're calling a function print on the output of another function, type. We use parentheses to define the order in which functions get run. What's contained in one set of parentheses needs to be evaluated first before being given as input to the next function. Here, the type function is run first, and then its output is printed. Different types have different properties, and when you're designing a computer program, you'll need to choose the types for your data based on how you're going to use them. For example, if you want to use a number as a part of a sentence, it'll be easiest if that number is a string. If you want to encode a true-false value, it will be much easier to manipulate as a Boolean than a string. Why is it easier? There are specially designed functions for working with each data type. You'll learn about these soon. You might also have situations where you don't control the type of data that you receive, but you still need to use it. The good news is that you can create new objects from old and change the type in the process. We went over this in the integers and floats video. For example, here we create an int from a float and assign it to a variable count. Here, we create a string out of the house number and use that to build a larger address string. First, we have the house number, as well as the street and town name. You can see that the house number is currently an int. We can change it to a string like this and use the plus operator to create the full address. You can also build a number from a string like this. Here, we start with a string of 35, but by wrapping it in a float function, we can see the type has now changed. So far, we've seen 2 distinct ways to process data with Python: operators and functions. We've used operators like these, which process the 2 values on either side of the operator. We've also used functions like print and len. Functions are very similar to operators. In fact, the only real difference is in how they look. Function inputs are put in parentheses rather than being placed next to an operator. And functions have descriptive names rather than short symbols. There is a third technique for operating on values: methods. The best way to learn about methods is with an example. Consider this title method. Methods are related to functions, but unlike functions, methods are associated with specific types of objects. That is, there are different methods depending on the type of data you're working with. In this example, the object is a string with the value Sebastian Thrun, and we are calling its title method. The method returns a string in title case, meaning the first letter of each word is capitalized. So methods are functions that belong to an object. An object, for example, being a string. Let's try another string method, isLower. The isLower method checks whether the characters in a string are lowercase. In this case, the string object is Sebastian Thrun. isLower returns true since there are no uppercase letters. You've probably noticed that when we call the isLower and title methods, we use parentheses, but we haven't put anything in them like we did when calling functions. Those inputs in the parentheses are called arguments. Since methods are special types of functions that belong to an object, the object is always the first argument to a method. So isLower and title actually did have an argument, although there was nothing in the parentheses. The argument is disguised as the string object. Let's try a method that takes more arguments than just the object: count. Here, the count method returns how many times the substring fish occurs in the string. The object is the string, one fish, two fish, red fish, blue fish. And the method is .count. And 4 occurrences of the word fish exist in the string. Congratulations on completing this lesson on data types and operators. You've started your journey in Python with a great foundation. Next, you'll learn how to piece together the building blocks you just learned to write cooler and more complex programs. Great job!
I would say Udacity definitely played a big part in helping me transform my career. Before I was in retail banking, the moment I realized that when I wake up in the morning, do I feel excited to go there, or is it just something that, hey, I got a job, I should just be grateful for the fact that I got a job.
I've been always drawn to creating things. So I studied multimedia computer science, and then I joined Mercedes, became a service manager for IT. In the recent years, there was some cultural change in my company. So there was a big data team created.
Data is everywhere, and more companies are hiring key people who can analyze and visualize data to make key decisions. Introducing Udacity's Data Analyst Nanodegree program. In this program, you will master the skills you need to establish a successful career as a data analyst. Our curriculum was developed with leading industry partners to ensure students gain the most valuable data analytical skills.
While I was in the nanodegree, I learned a lot. I think it's more of how to look at data in a different way. The projects I'm doing, they're actually more helpful. I know those skills that I acquired can actually help me with getting employed.
So what changed in my professional life was that I was able to convincingly show people that this is something I am now a specialist in. Now I'm becoming an architect for data science at Mercedes.
Well, when I got that job offer, that was the best feeling ever. And Udacity actually, made that happen.
Welcome to this lesson on data structures. So far, you've dealt with variables representing individual basic data types, like integers, floats, booleans, and strings. In this lesson, you'll learn how to group and order these data types into different data structures, namely lists, tuples, sets, dictionaries, and compound data structures. You'll also learn about the last 2 types of operators in Python, membership and identity, along with more built-in functions and methods. Let's get started. We've seen individual pieces of data, like a string or a number. These are great, but Python's capability to write powerful programs is maximized when we can work with something called containers of data, which contain other data types and even other containers. So let's introduce our first Python container, lists. A list is a data structure in Python that is a mutable, ordered sequence of elements. More on the mutable ordered part later. This code defines a variable, months, which contains a list of strings. Each element in the list is a month of the year. A list is defined using square brackets and always holds other data which are separated by commas. This data could be a mix of any of the data types you have already seen. Lists have an order, or more appropriately, are ordered. We can look up individual elements in the list by their index. We can look up values in a list like this. We type in the list name, followed by square brackets, with an integer indicating its position, or index. Notice that the first element in the list, January, is located at index 0 rather than index 1. Many programming languages follow this convention, called zero-based indexing. If zero-based indexing is confusing, consider it this way. An element's index describes how far the element is from the beginning of the list. The first element is 0 elements away from the beginning. The second one is 1 element away, and so on. We can also index from the end of the list rather than the front like we've been doing so far. To do this, we use negative indices. For example, we can get the last month of the year. The index -1 refers to the last element of the list, -2 to the second to last, and so on. Note that while 0 is the first index of the list, -0 is not the last, which can be a bit confusing. If you attempt to access an index in a list that does not exist, you will get a list index exception. This is Python's way of telling you that you are trying to access an index that is not in the list. Since the index 25 does not exist, we received this error. Getting index errors is quite common, especially if you're not used to indexing in Python. You might get these errors quite a lot in the beginning. The most common reason for getting an index error is using an index that's off by 1. But there may be other reasons why you would get such an error. It is always a good idea to use the print function and debug with a small example. This can tell you if your indexing is off and by how much. In addition to accessing individual elements from a list, we can use Python's slicing notation to access a subsequence of a list. Slicing means using indices to slice off parts of an object, like a string or a list. An example makes it super clear. Again, consider this list of months. We can slice the third quarter of the year from the months list like this. The index to the left of the colon, 6, is where the slice begins. The slice continues up to the second index, 9. Notice that the 6 is the index of July, but 9 is the index of October. The lower bound is inclusive, but the upper bound is exclusive. There are a couple of slicing shortcuts that simplify common situations. If you would like to make a slice that begins at the very beginning of the original list, you can omit the starting index like this. Or, if you'd like to make a slice that ends at the very end of the original list, you can omit the ending index like this. List is a type, just like string, float, and int. Of the types we've seen, lists are most similar to strings. Both types support the len function, indexing, and slicing. Here, you can see that the length of the string is the number of characters, and the length of the list is the number of elements it holds. And zero indexing is supported for both, as well as slicing based on the indices shown here. Another thing they both support are membership operators, in and not. In evaluates if the object on the left side is included in the object on the right side, and not in evaluates if the object on the left side is not included in the object on the right side. Here, we can check if the string her is in this string, which is right here. However, Sunday is not in our list, as it only holds the months. So how are lists different from strings? You saw that both support indexing, slicing, and the in operator. The most obvious difference is that strings are sequences of letters, while list elements can be any type of object. A more subtle difference is that lists can be modified, but strings can't. Here, we can change the fourth element, index 3, of this list to Friday if we want. But here, we get an error if we try to change the third element of a string. The technical term for whether an object can be modified after its creation is mutability. We can modify the values of lists, so a list is a mutable data type. We can't modify strings, so a string is an immutable data type. As we introduce more data types, there are two factors that we will continue to consider. One is mutability, and the other is order. Order is whether the order of contents for an object matters, and whether or not parts of the object can be accessed using this order. Both strings and lists are ordered, which is why indexing works well for them. However, one is mutable, while the other is not. We will see more data types that fall under different sections of this grid as we continue. For now, we'll explore the methods and functions that work on lists, and we'll take advantage of list mutability in our programs. Previously, when we created a variable that held an immutable object, the value of that immutable object was saved in memory. Here, we create a name with value Jim and assign it to another variable called student. It is the value Jim that is assigned to student. So when we reassign name to update it to Tim, this change is not reflected in the value of student. Lists are different from strings as they are mutable. Here, we create a list of scores and assign this same list to the variable grades. B, C, A, D, B, A. 6 of them. And when we change or mutate the scores list, making the 4th grade B instead of D, this affects both scores and grades. Both scores and grades are variable names for the same underlying list, and either name can be used to access and change that list. The behavior of variables containing mutable and immutable objects are very different and might even seem surprising at times. Experiment. Use the print functions and double-check your work where you can to make sure that your programs correctly keep track of their data. While you experiment with lists, there are some useful functions you should get familiar with. Len returns how many elements are in a list. Max returns the greatest element of a list. How the greatest element is determined depends on what type of objects are in your list. The maximum element in a list of numbers is the largest number. The maximum element in a list of strings is the element that would occur last if the list was sorted alphabetically. That's reticulated Python for this list. R is the largest letter alphabetically. In other words, greater than B, A, B, and A. This works because the max function is defined in terms of the greater than comparison operator. The greater than comparison operator is defined for many non-numeric types. If you're working with objects that can be compared with this, then you can use max on a list of the objects. For strings, the standard comparison is alphabetical, so the maximum of this list is the element that appears last alphabetically. Although you can create lists that hold a mix of elements of many types, as you see here, integers and text, the max function is undefined for lists that contain elements from different incomparable types. Here, you can see it breaks with this mix of data types. Min is the opposite of max and returns the smallest element in a list. Sorted returns a copy of a list in order from smallest to largest, leaving the original list unchanged. Here, for a list called sizes, the order is ascending. You can sort from largest to smallest by adding the optional argument reverse equals true. Now the order is descending. Let's introduce a new string method that works with lists. Join. Join takes a list as an argument and returns a string consisting of the list elements joined by a separator string. In this example, we use the string \n as a separator so that there is a new line between each element. For, new line, aft, new line, starboard, new line, port. We can also use other strings as separators with join. Here, we use a hyphen. It's important to remember to separate each of the items in the list you are joining with a comma. Forgetting to do so will not trigger an error, but will also give you unexpected results. In the example below, omitting a comma between Garcia and O'Kelly results in the following. Notice how the hyphen separator is missing between Garcia and O'Kelly, and instead the two strings were appended. This happens because of Python's default string literal appending. If join returns different results than expected, check for missing commas. Also, note that join will trigger an error if we try to join anything other than strings. We get an error here because an integer was included in the list. Lastly, a helpful method called append adds an element to the end of the list. Next, you'll practice working with lists and explore more list methods. Python provides another useful container, tuples. Tuples are used to store related pieces of information. A tuple is a data structure in Python that is an immutable, ordered sequence of elements. Consider this example involving latitude and longitude. Tuples are similar to lists in that they store an ordered collection of objects which can be accessed by their indices. For example, location 0 and location 1. Unlike lists, however, tuples are immutable. You cannot add or remove items from tuples or sort them in place. Why do we have tuples if they're like lists with fewer features? Tuples are useful when you have two or more values that are so closely related that they will always be used together, like latitude and longitude coordinates. Tuples can also be used to assign multiple variables in a compact way. Notice that the values assigned to the tuple dimensions aren't surrounded with parentheses as previous examples were. The parentheses are optional when making tuples, and programmers frequently omit them if parentheses don't clarify the code. In the second line, 3 variables are assigned from the content of the tuple dimensions. This is called tuple unpacking. You can use tuple unpacking to assign the information from a tuple into multiple variables without having to access them one by one, and make multiple assignment statements. In this example, if we won't need to use dimensions directly, we could shorten those 2 lines of code into a single line that assigns 3 variables in one go. Imagine that you run a popular search engine and you've surveyed your users to see where they're browsing from. You've collected the 785 responses and have assembled them into a list of countries. There aren't 785 countries in the world, which means that there are duplicate entries in the countries list. Slicing the list to see the first few elements confirms this. It would be useful to remove the duplicates to produce a list of all of the countries that users browse from. Well, a set in Python does exactly that. Sets are containers of unique elements without any particular ordering. We can create a set from a list like this. Set removes the duplicates, and the print function prints the unique values, of which there are 196 countries. Sets support the in operator the same way lists do. India is in this set. You can add elements to sets, but you don't use the append method like you do with lists. Instead, sets have the add method. Here, Italy is added. Sets also have a pop method, just like lists. When you pop an element from a set, a random element is removed. Remember that sets, unlike lists, are unordered, so there is no last element. Other operations you can perform with sets include those of mathematical sets. Methods like union, intersection, and difference are easy to perform with sets and are much faster than such operators with other containers. Sets are simple data structures, and they have one main use: collecting unique elements. Our next data structures, dictionaries, are more flexible. Rather than storing single objects like lists and sets do, dictionaries store pairs of elements, keys, and values. In this example, we define a dictionary where the keys are element names and their values are their corresponding atomic numbers. We can look up values in the dictionary by using square brackets enclosing a key. We can also insert new values into the dictionary with square brackets. Here, we are adding lithium and giving it a value of 3. Dictionary keys are similar to list indices. We can select elements from the data structure by putting the key in square brackets. Unlike lists, dictionaries can have keys of any immutable type, not just integers. The element dictionary uses strings for its keys. However, it's not even necessary for every key to have the same type. We can check whether a value is in a dictionary the same way we check whether a value is in a list or set with the in keyword. We can use in to verify whether a key is in the dictionary before looking it up, if there's a possibility that the key is not there. Mithril was not part of our elements dictionary, so false is printed. Dictionaries have a related method that's also useful: get. Get looks up values in a dictionary, but unlike square brackets, get returns none, or a default value of your choice, if the key is not found. The lithium is not in our dictionary, so none is returned and then printed. If you expect lookups to sometimes fail, get might be a better tool than normal square bracket lookups because errors can crash your program, which isn't good. You can check if a key returned none with the is operator, or you can check for the opposite using is not. These are called identity operators. You will learn more about identity operators and how they differ from using these equals to or not equals to comparison operators in the quizzes that follow. In the elements dictionary we saw earlier, element names, which are strings, are mapped to their atomic numbers, which are integers. But what if we wanted to store more information about each element, like their weight and symbol? We can do that by adjusting this dictionary so that it maps the element names to another dictionary that stores that collection of data. We can look up information about an entry in this nested dictionary in the same ways we did before, with square brackets or the get method. We can look up specific information from the helium dictionary like this. This code is first looking up the key helium in the elements dictionary, producing the helium dictionary. The second lookup, weight, then looks up the weight key in that helium dictionary to find helium's atomic weight.
Whether you want to be a web developer, a machine learning engineer, or a data scientist, having a clear understanding of data structures and algorithms is key to acing your job interview. From evaluating which data structure to use when you're building out a website, to selecting the right algorithm for analyzing user data, every computer science problem requires an intuitive understanding of the tools you have at your disposal.
Companies don't hire candidates who can just rattle off the names of different data structures and algorithms, but instead the ones who can choose the right approach to solving a particular problem and provide a rationale for their choice.
The Data Structures and Algorithms Nanodegree program will enable you to excel at solving everything from very well-defined problems, like how to calculate the efficiency of a specific algorithm, to more open-ended problems, like building your own private blockchain or writing a web crawler.
Whether you're new to the ideas surrounding data structures and algorithms, or just looking to refresh on a few concepts before your next interview, this program will provide you with a wealth of valuable practice and resources.
Throughout the program, you'll have a dedicated mentor who will support you with one-on-one guidance and help you solidify your understanding of these exciting topics.
Join the Data Structures and Algorithms Nanodegree program today, and you will get to work on over 100 exercises and real-world projects. Learn how to approach open-ended problems and design and implement your solution. This Nanodegree program will prepare you for your next coding interview to launch your career as a software engineer.
Welcome to this lesson on control flow. Here, you'll learn how to add more functionality to your code by being able to use conditional statements and loops. You'll learn how to implement decision-making with if statements, repeat code with for and while loops, exit or skip loops with break and continue, use helpful built-in functions like zip and enumerate, and combine some of these concepts in concise list comprehensions. With these tools, you'll be able to bring together the data types and operators you learned from the previous lesson in more complex and creative ways. Let's get started. We've been running code that simply executes every line one by one from the top down. Many times, however, we want to run code only if a particular condition holds. To demonstrate this concept, let's take a look at this billing system for a pay-as-you-go mobile phone. Say a customer has a credit balance for their phone, which they can use for calls and messages. The customer can then set up a link to their bank account so that if their phone credit balance goes below a threshold amount, in this case $5, then $10 more of credit are added and their bank balance is billed. Here is a simple way of representing this billing system in code. If the phone balance is below 5, add 10 to phone balance and subtract 10 from bank balance. This is an example of an if statement. An if statement is a conditional statement that runs or skips code based on whether a condition is true or false. In an if statement, the if keyword is followed by the condition to be checked, in this case phone balance less than 5, and then a colon. The condition is specified in a Boolean expression that evaluates to either true or false. After this line is an indented block of code to be executed if the condition is true. So in this case, these lines will only execute if it is true that phone balance is less than 5. If phone balance is 3, this condition evaluates to true, and these indented lines of code are executed. You can observe these changes in the output. If phone balance is 8, however, this condition evaluates to false, and these lines are not executed. As you see in the output, there were no changes to phone or bank balance, which is what we expect to happen since the condition in this if statement was false. Now you know how to execute a block of code if a condition is true. But what if you have a different block of code that you want to execute when that condition is false? You can use the else keyword to do so. Consider this code, which prints a message indicating whether an integer n is even or odd. If n is even, this line is run. Otherwise, this line is run. Code indented under the else is what happens when this condition evaluates to false. The else keyword is always followed by a colon and doesn't need a Boolean expression. So, if we set n to be 4, like this, the if statement here would evaluate to true, and we would print the following string. Alternatively, if we set n to be 15, this condition would evaluate to false, so we would skip this block and execute the code under the else. If you have more than 2 possible cases, you can also use elif, short for else if, to deal with this situation. This saves the multiple indentation that would be needed if we used else and then another if statement inside the else block. Like if, an elif statement always requires a conditional expression. For example, let's say we wanted to print what to do with the garden based on the current season. If we set season equal to spring, like this, then we can see that plant the garden is printed, as this first condition evaluates to true. Alternatively, if we set season to winter, then each of these conditions will evaluate to false until we hit this condition, which will evaluate as true, and print stay indoors. Notice here we are using double equal sign again. Remember, a single equal sign is for assignment, like we did here when we were setting a season as a particular string. 2 equal sign is for evaluation, where we are evaluating a condition as true or false. As you have just seen, indentation is important. It's how we tell Python what code is in the body of an if statement and what code is outside of it. Indentation doesn't just matter in if statements. Soon, you will see it used in other contexts. Some other languages use braces to show where blocks of code begin and end. In Python, we use indentation to enclose blocks of code. This indentation conventionally comes in multiples of 4 spaces. It's important to be strict about following this convention because changing the indentation can completely change the meaning of the code. If you are working on a team of Python programmers, it's important that everyone follows the same indentation convention. All of the if and elif statements we've seen so far have been followed by a single Boolean expression that checks only one condition. However, more complicated Boolean expressions can be useful as well. If the condition is working with a numerical variable, you might want to check whether a value lies in a certain range, or even do some calculation in order to make a comparison. Notice this condition uses logic and algebra and will still run correctly in Python. Storing values for height and weight, we can quickly print the result for any individual. Some situations may call for logical operators. If it's rainy and sunny, I might look for a rainbow. Notice that the if statement here requires that both of these individual variables hold true to evaluate as true. If either is false, then this line will evaluate as false, and our print statement will not run. Let's say I want to send a promotional email to a customer if they have not requested to be taken off the email list and they're in a location where they'll be able to redeem the offer. For really complicated conditions, you might need to combine some ands, ors, and nots together. Use parentheses if you need to make the combinations clear. However simple or complex, the entire line in an if statement must be a Boolean expression that evaluates to either true or false. And it is this value that decides whether the indented block in an if statement executes or not. We'll go over some good and bad examples of Boolean expressions used in if statements. While true is a valid Boolean expression, it's not exactly useful as a condition, as it always evaluates to true. So the indented code will always get run. Similarly, if false is not a condition you should run either. The condition in the if statement would never occur. In this example, is cold or not is cold will always evaluate to true. If it is cold, then is cold will be true. If it is not cold, then not is cold will be true. This has no use as a condition because the indented code will always get run. This code is valid in Python, but it is not a Boolean expression, although it reads like one. The reason is that the expression to the right of the or is not a Boolean expression. It's a string. Later, we'll discuss what happens when you use a non-Boolean type object in place of Booleans. It takes a few more characters, but this is now unambiguously a Boolean expression. The expressions on both sides of the logical operator OR are each checking something. This is a valid condition, but we could express it more briefly and clearly. Is cold is a Boolean expression on its own right, so we can make the code more readable by using the variable itself instead. If you want to check whether a Boolean is false, you can use the not operator. Let's summarize the lessons from these examples. True and false are both Booleans, but it doesn't make sense to use if true or if false. Logical operators and, or, and not have specific meanings that aren't quite the same as their meanings in plain English. Make sure your Boolean expressions are being evaluated the way you expect them to. Don't compare a variable that is a Boolean with equals true or equals false. This comparison isn't necessary since the variable itself is a Boolean expression. So far, the conditions we've used were Boolean expressions that evaluate to a Boolean object, either true or false. If we put some other object that is not a Boolean in the if statement, Python will check for its truth value and use that to decide whether or not to run the indented code. Here, the condition is an integer variable and evaluates to true. The Python documentation lists all the objects that are considered false in this situation. Anything that isn't listed as having a truth value false will evaluate as true. In this code, errors has the truth value true because it's a non-zero number, so the error message is printed. This is a nice way of writing a succinct if statement. Similarly, in this example you saw earlier, the string in the second part of this condition will evaluate to true. So this statement will always evaluate to true regardless of what value is stored in weather. Alternatively, this will evaluate to true if weather is the string snow, and will evaluate to false if weather is any other string. However, these types of conditions aren't really common knowledge and are not common in practice. Now that you've learned about conditional statements, let's move on to loops, which allow us to repeat blocks of code. Python has two kinds, for loops and while loops. Let's first take a look at the for loop, which we can use to iterate over an iterable. An iterable is an object that can return one of its elements at a time. This can include sequence types, such as strings, lists, and tuples, as well as non-sequence types, such as dictionaries and files. You can define objects with an iter method to allow them to be used as an iterable, which you can find more information on in the notes below. Consider this for loop that iterates through a list of cities, capitalizes each one, and prints it. The for keyword signals that this is a for loop. Cities is the iterable, and city is the loop's iteration variable. That is, the variable that represents the element in the iterable that the loop is currently processing. So in the first iteration, city would be New York City. In the second iteration, it would be Mountain View, and so on. We can use the city variable to refer to an element within the indented body of a for loop during any iteration. This indented body is executed once for each element in cities. You can name iteration variables however you like, though this example demonstrates a common pattern. The name of the list cities is the plural form of city, the name of the iteration variable. Naming lists and iteration variables in this style makes it easier for other programmers to understand the purpose of each variable. So far, the loops we've written extract information from lists. We can also use for loops to create lists and to modify lists. To create a new list, we can start with an empty list and then use the append method to add new items. This for loop iterates through each city in cities and appends it to capitalized cities. Modifying a list is a bit more involved and requires the use of a new function, range. Range is a built-in function used to create immutable sequences of numbers. It has 3 arguments which must all be integers: start, stop, and step. Start is the first number of the sequence. Stop is 1 above the last number of the sequence. And step is the difference between the numbers in the sequence. If unspecified, start defaults to 0 and step defaults to 1. Calling range with 1 integer will make that the stop argument and return a sequence of numbers from 0 to that integer minus 1. So range 4 returns 0 through 4 minus 1, which is 3. Calling range with 2 integers will make those the start and stop, and return a sequence of numbers from the first number to the second number minus 1. Range 2, 6 returns a sequence from 2 to 5. Calling range with 3 integers will return a sequence of numbers from the first to the second minus 1, separated by the third. So range 1, 10, 2 returns a sequence from 1 to 9, incremented by 2. Notice in these examples, we wrapped range in a list before printing it. This is because printing just the output of range only shows you a range object. You can view the values in the range object by converting it to a list or iterating through it in a for loop. Back in our cities example, we can use the range function to generate the indices of each value in the cities list. This lets us access the elements of the list with cities bracket index, so that we can modify the values in the cities list in place. Let's go through one iteration of this to show exactly how all these pieces work together. Len cities provides 4, so the list will be a range from 0 to 3. The index will take on each of these values one at a time. So this first iteration will have an index of 0. This part here will then index the first city, New York City, capitalize it using title, then place it back in place of the original New York City spot. This same process would then occur for each of the additional cities. We can use print to see the change in the cities list at each iteration. By getting a list of indices with the range function, we were able to index into each element of a list in a for loop to apply a change. While list modification is one application of the range function, that isn't the only thing it's useful for. you will frequently use range to repeat an action a certain number of times. For loops are an example of definite iteration, meaning that the loop's body is run a predefined number of times. A for loop over a list executes the body once for each element in the list. A for loop using the range function will execute the number of times specified by the range function. This differs from indefinite iteration, which is when a loop repeats an unknown number of times and ends when some condition is met. Consider this while loop that simulates a blackjack dealer by drawing cards from a deck list into a hand list, stopping when the value of the cards in the hand is 17 or more. This example features a new function, sum, and a new list method, pop. Sum is pretty intuitive. It returns the sum of the elements in a list. Pop is the inverse of the append method. It removes the last element from a list and returns it. You can read more about this in the official documentation. In this line, we are computing the sum of the list hand and checking if that is less than or equal to 17. In this line, we are popping the last element from card deck and appending that to the hand list. Let's talk about how this while loop works. The while keyword indicates that this is a while loop. Next is the condition. In this example, sum hand is less than or equal to 17. If this condition is true, the loop's body will be executed. Each time the loop's body runs, the condition is evaluated again. This process of checking the condition and then running the loop repeats until the expression becomes false. The indented body of the loop should modify at least one variable in the test expression. If the value of the test expression never changes, the result is an infinite loop. In this example, the loop's body appends numbers to the hand list, which increases the value of sum hand. Eventually, the value of sum hand becomes large enough that the condition becomes false. For loops iterate over every element in a sequence, and while loops iterate until their stopping condition is met. This is sufficient for most purposes, but we sometimes need more precise control over when a loop should end. In these cases, we use the break keyword. A loop will terminate immediately if it encounters a break statement. We can use this to end the loop if we detect that some condition has been met. The break keyword can be used in both for and while loops. For example, suppose you want to load a cargo ship with a list of items called manifest. This list contains tuples of items and their weights. Ideally, you would like to load all the items on the ship, but the ship has a maximum weight capacity. Therefore, when the ship's capacity is reached, you want to stop loading. To accomplish this, let's use a for loop, loading each item and keeping track of the weight of all the items we have loaded so far. Here, we check if the ship's total cargo weight reaches its maximum capacity of 100 with each addition of cargo. If it does, we use a break statement to stop loading. If not, we load the next item and add on its weight. Here's what we end up loading. That's not good. The boat is severely over its weight limit of 100. The break statement did prevent us from putting every item on the boat, but we still exceeded the limit by 111. It's difficult to see what's gone wrong. One strategy we can use is to add print statements in the code. This is a really handy technique as it can give us some insight into what happens in the code as it's running step by step. Having print statements frequently that give context can really assist us in understanding what went wrong here. Here's the loop with debugging statements added. Debugging is the process of identifying and removing errors in your code. Here, we can see that we didn't break until the weight exceeded 100, when really we should break before that item is added. Additionally, we can see that the cheeses still could have fit if the machine wasn't added. This brings us to another statement. Sometimes, rather than breaking out of the loop completely, there will be times we want to skip simply one iteration of the loop. In this case, we would use the continue keyword. In this example, we iterate through a list of foods and increment a count if the food is a fruit. Here, we terminate an iteration if the food is not found in fruit. Otherwise, we add 1 to fruit count. So when food is hummus or toast in this loop, the rest of the loop is completely skipped. Looking back at our list of cargo, notice each element is a tuple of size 2. Iterating through a list with multiple values can be pretty helpful. It's actually really easy to combine and split lists like this. If we originally started with these two separate lists, items and weights, and wanted to combine them to create a list like manifest, we can use a built-in function called zip. Zip returns an iterator, so we need to convert it to a list to see the elements, or iterate through it with a for loop if we want to print the values, similar to range. You could also unpack each tuple in a for loop like this. In addition to zipping two lists together, you can also unzip a list using an asterisk. For example, using the manifest list like this, you can separate it into an items and weights list like this. The next function we'll look at is enumerate. Many times, you'll find it useful to iterate through the values of a list along with the index. This is one way you could do it. This uses a for loop to iterate through a list of tuples containing the index and value of each item in the list. The indices are created by getting a range object from 0 to the length of items minus 1 and zipping that with the values in items. Enumerate is a special built-in function that makes this a lot simpler. Enumerate returns these tuples containing the indices and values of a list in an iterable for you. You'll be getting some practice using zip and enumerate and see how helpful they can be in the following quiz section. In Python, you can create lists really quickly and concisely with a cool tool called list comprehensions. In the cities example from earlier, we created a list of capitalized cities from the cities list in a for loop. With a list comprehension, we can get the same result like this. List comprehensions allow us to create a list using a for loop in one step. You create a list comprehension with brackets, including an expression to evaluate for each element in an iterable. This line calls city.title for each element in cities to create each element in the new list. Notice this part looks just like the first line of a for loop without a colon. And the action we want to take on each element is taken on the element here and appended to this new list. In a list comprehension, we don't need to create a new list beforehand and append to it like we would in a for loop. List comprehensions are not found in other languages, but are very common in Python. Here's another example that creates a list of squares from 0 to 64. This line calls x to the power of 2 for every element in range 9 to create each element in the new list, squares. We can write this as a list comprehension like this. Again, we are just looping through each element in this iterable and evaluating this expression to get each new element in our list. You can also add conditionals to list comprehensions. After the iterable, you can use the if keyword to check a condition in each iteration. In this example, x to the power of 2 is only evaluated if x is even. This gives us a list only including squares of even numbers. If you want to add an else, you will get a syntax error doing this. If you would like to add else, you have to move the conditionals to the beginning of the list comprehension, right after the expression like this. Details on why this is the case are in the notes below. Congratulations on completing this lesson on control flow. You learned how to use conditional statements, loops, useful built-in functions, and list comprehensions to add more functionality to your code. Next, you'll learn how to organize your code into functions. Great job! Welcome to this lesson on functions. Previously, we used several of Python's built-in functions. Here, we will write functions of our own. Functions are useful chunks of code that allow you to encapsulate a task. Encapsulation is a way to carry out a whole series of steps with one simple command. For example, imagine you want to bake a cake. You would need to buy the ingredients, mix them together in a certain way for specific amounts of time, put it all in the oven, and then let it cool. In computer programming, functions encapsulate all the steps of a process into one command. In this case, we might just have a bake cake function and throw all of these directions into this one function. Now, anytime we want to bake a cake, we just use this function without worrying about all of the specifics. Functions are also used to help organize and optimize code. Let's get started. As our first function, we'll write a function that calculates the volume of a cylinder. The formula for this is the cylinder's height multiplied by the square of its radius multiplied by pi. Here's what that formula looks like when defined in a function called cylinder volume. After defining the cylinder volume function, we can use it like this. This value is the volume of a cylinder 10 inches tall with a radius of 3 inches. Let's see how this works behind the scenes. A function definition includes several important parts. First, let's look at the function header. Defining a function always starts with the def keyword to indicate that the code that follows is a function definition, and ends with a colon. Following def is the name of the function, in this case, cylinder volume. This needs to be one word with no gaps. That's why this has an underscore. The rules for function names are the same as those for variable names. If you need a reminder on this, see the text below this video. After the function name are parentheses that enclose the arguments that the function expects, separated by commas. These arguments are values that are passed in as inputs when the function is called, and are used in this body. If you write a function that doesn't take arguments, then just leave these parentheses empty. Here is an example of a function that takes no arguments. In this case, there is no input data we want to work with in the body of the function, so no arguments are necessary. Next, let's discuss the body of a function. The body of the function is indented after the header, and is where the function does its work. Within this body, we can refer to the argument variables and define new variables. The pi variable that we define here is a local variable, meaning it can only be used within the body of this function. Attempting to access this variable outside the function isn't possible. This is due to what is called variable scope, which determines which variables you have access to in Python. We'll discuss this in detail later in the lesson. Often, the body of a function will include this return keyword, which is used to give back an output value when the function is called. The value of the expression that follows return is the output of the function. In this example, we return the value evaluated from this formula for the volume of a cylinder. Rather than returning the value as it is calculated, an alternative technique would be to calculate the volume earlier in the function body and then store it in a variable named volume. In this case, we would return volume like this. Functions like this can be imagined as little machines that take inputs or arguments and process them into output or return values. This is a good image, but it's incomplete. Some functions, like print, don't return anything at all. Print displays text on the output window, but as we see here, the value it returns is none. None is what a function will return by default if it doesn't explicitly return anything else. The difference between print and return is often confused. Print provides output to the console, while return provides a value that you can store and work with in code later. You will get some practice with this in the quizzes that follow. It's not necessary that every function has a return statement. Notice this function, print greeting, doesn't have a return statement, but it's still a valid function. Let's revisit the cylinder volume function, but with one modification. This function includes a default argument. If radius is not specified, then the variable radius will default to 5 when used in the function body. Calling the function like this would be the same thing as calling it like this, because radius is set to 5 if not specified as another value. Default arguments allow functions to use default values when those arguments are omitted. This is helpful because it can make your code more concise in scenarios where there is a common value you can use for a variable, although you still want it to be customizable. In this example, the default radius is 5, but we can still change this. This time, when we call the function, we are overriding the default value of 5 and calculating the cylinder volume for a cylinder with a radius of 7 instead. Also notice here we are passing values to our arguments by position. It's possible to pass values in two ways, by position and by name. Each of these functions is evaluated in the same way. This one is simply taking the arguments by position, while this function is accepting arguments by name. There are some nuances for when you can perform the passing of values in each of these ways. You'll see more applications of this in the following quiz sections. Scope refers to which parts of a program a variable can be referenced or used from. If a variable is created inside a function, it can only be used within that function. Consider these two functions, word count and nearest square. The first function uses answer to count words in a document. The second function uses answer to track values while searching for the nearest square. Both functions include this answer variable, but they are distinct variables that can only be referenced within their respective functions. Alternatively, we might have a variable defined outside of functions, like this, and we can access it anywhere outside or within these functions. Scope is essential to understanding how information is passed throughout programs in Python and really any programming language. One of the key advantages of functions is that they can help break a program down into smaller chunks. This makes code easier to write and also easier to read because the pieces of your code, the functions, are reusable. If a program needs to calculate volumes of multiple cylinders, it can call this cylinder volume function multiple times, which is much cleaner than writing out the formula over and over again. Functions make code easier to read because they give human-readable names to processes. While the cylinder volume formula isn't that complicated, it is still harder to recognize than a precisely named function. There is an additional technique that makes functions more readable: documentation strings, or docstrings. Docstrings are a type of comment used to explain the purpose of a function and how it should be used. Here is a function for population density with a docstring. Docstrings are surrounded by triple quotes. The first line of the docstring is a brief explanation of the function's purpose. If you feel that this is sufficient documentation, you can end the docstring here. Single-line docstrings are perfectly acceptable. If you think that the function is complicated enough to warrant a longer description, you can add a more thorough paragraph after the one-line summary. The next element of a docstring is an explanation of the function's arguments. Here, you list the arguments, state their purpose, and what types the arguments should be. Finally, it's common to provide some description of the output of the function. Every piece of the docstring is optional. However, docstrings are a part of good coding practice. They assist you and future users in understanding the code you produced. You can read a more thorough explanation of docstring conventions in the link below. In Python, you can use lambda expressions to create anonymous functions. That is, functions that don't have a name. They are very helpful for creating quick functions that aren't really needed later in your code. Later, we'll learn about higher order functions, or functions that take in other functions as arguments, where lambda expressions become especially useful. Let's compare the structure of a function and a lambda expression. Here is a simple function that doubles a number. It takes in a number x and returns x multiplied by 2. Calling double 3 would return 6. Here is the equivalent in a lambda expression. The lambda keyword is used to indicate that this is a lambda expression. Following lambda are one or more arguments for the anonymous function, and then a colon. These are equivalent, similar to the way argument names in a function are arbitrary. Last is an expression that is evaluated and returned in this function. This is a lot like the expression you might see as a return statement in a function. With this structure, lambda expressions aren't ideal for complex functions, but can be very useful for short, simple functions. If you want to specify multiple arguments in a lambda function, you can include them before the colon, separated by commas. Here's a lambda function that multiplies two numbers together. In the following quizzes, you'll get some practice using lambda functions and see how useful they can be. Congratulations on completing this lesson on functions. You learned about functions, variable scope, documentation, lambda expressions, iterators, and generators. Next, you'll learn how to write scripts in local environments with many functions pieced together. That's a lot of stuff. It's okay if you haven't mastered everything yet. You've already accomplished a ton by getting this far. We'll practice more of these concepts in the next lesson. Welcome to this lesson on scripting. Here, you'll learn how to combine all of the concepts you've learned throughout this course to write and run your own scripts locally on your computer. You'll learn about good scripting practices, working with raw input from users, reading and writing files, handling errors, importing local scripts, and working with different libraries. Let's get started. In all of the previous lessons, we've been using these boxes to represent a code editor where we wrote our Python code, and output window where we viewed results. And in the classroom, you use these programming quizzes to write Python and run your code. But instead of running your code online in the classroom, you can run Python on your own computer by installing Python and useful tools for your programming environment. Since Python is a popular open source programming language, it's free to download, change, and use. And the fact that it's already popular means there are online instructions to help you get it installed for most common operating systems. Because it's popular and open source, there's a large global community working on developing Python. For you, as a Python user, that means there will be new versions coming out as Python is improved by the community. You might find yourself needing to update Python from time to time, especially if you're collaborating with other people as you write Python programs that are compatible with the version they're using. Now, it's time for you to install Python. Now that you've successfully installed Python, let's try to run a script in your terminal. First, download the file firstscript.py attached at the bottom of this page and move it to an appropriate directory. I put my file here by dragging it from the Downloads folder to this folder. This might be a good time to set up a new directory for your learning if you don't have one already. Next, open your terminal and use cd to navigate to the directory containing the downloaded file. I can double check that the file is located here by typing ls or dir on Windows. Now that you're in the directory with the file, you can run it by typing Python followed by the name of the file like this. Then press enter. You'll know you've run the script successfully if you see this message. Whenever you type Python followed by the file name for a Python script, that script is run and the output is shown immediately afterwards. Once the code's finished running and all the output has been shown, your command line prompt reappears. Note if you type and enter just Python without a script to run, it'll start an interactive interpreter for Python. You'll learn more about this later. For now, you can just type in exit with parentheses to get out. Or alternatively, Control D on Mac and Linux, or Control Z and Enter on Windows. Now I'm back to the command line prompt. It's your turn. Download the file below and run the script in your terminal. There are many ways to set up a programming environment, and there isn't a right or wrong way to go about it. However, if you're just starting out programming in Python, you might like to see this setup to get some ideas. Over here is a text editor. This particular editor is called Atom, but there are many additional editors I recommend in the notes below. A text editor is really different from a word processor, so don't mix them up. Code needs to be written line by line with intentional line breaks and indentations that fundamentally change how the code is read and run. Good text editors have simple but vital features such as line numbers and syntax highlighting. You can see the different ways Atom highlights a text based on the types of words and objects it recognizes from the Python language. Syntax highlighting really helps make code more readable and organized. It can also prevent us from making some syntax errors. For example, if I forgot a quote at the end of this string, I'll know I missed it when the rest of the line is highlighted like a string. Atom knows to use syntax highlighting for Python because of this .py at the end of the file name. This tells Atom it's dealing with a Python file. Editors are highly customizable to suit your style. One setting that I use is soft tabs with a tab length of 4, which means that when I press tab, it's converted into 4 spaces. You can also add cool add-ons, like this Python linter that uses pylint to point out helpful things in my code. For example, in this line, pylint gives me a warning because I'm not following PEP 8 guidelines by including a space before my closing bracket. I also have this cool add-on which lets me use my terminal in my editor. Atom isn't the only thing on my screen right now. I do use this terminal add-on from time to time, but generally, I like to have a separate window for my terminal where I can run my scripts. Generally, I can't write a whole lot of code in one go because something will go wrong and I'll need to find the issue and debug it. When there's an error, it will show up here when I run the script. I make small changes to the code in the text editor and then run the script again to see the output. If I see a problem, I'll try to fix it, or if things seem to be working, I'll move on. I've also got the Udacity Classroom and results from a question I Googled in my browser. Normally, I'll need a browser open to look up documentation or search for the solution to a bug I encounter along the way. From now on, we recommend that you try out all your code in this way. Put code into a new file in your text editor, and don't forget the .py extension. Make sure you're in the correct directory in your terminal, and then run your script. Now that you have your local programming environment all set up, it's time to try out different inputs. Programs can get a lot more interesting when they can interact with external information. First, let's try getting raw input from the user. Here's what I mean. This program prompts the user to enter a name and takes in that input as a string to use in its code. This input function is what takes in the user's input as a string. It has an optional argument that you can use to specify a prompt shown to the user. Since the input function interprets input as a string, you'll need to wrap the result with int or a float if you want to use it as a number. If you don't do this and try to use the input as a number, you'll get an error. Here, I wrapped the input with int and added 20 to it. But what if the user inputs a non-integer number? You can just wrap it as a float to catch non-integer numbers as well. But what if you need an integer, like if you're multiplying a string by it to repeat it a certain number of times? This wouldn't work with the float even if it's an integer number. We can actually wrap this int with float and then convert it into an int like this. Okay, that works. Clearly, trying to imagine and handle every possible case with user input can quickly get complicated. We addressed some cases here, but there are also loads of other cases we didn't address that could lead to more errors. We'll learn a better way to handle these scenarios in the next section. Before we move on to practice, here's another way we can interpret user input. Eval is a built-in function that evaluates a string as a line of Python. You can even include variables in the string like this. Now let's write some fun scripts that interact with user input. As you saw in the last video, trying to handle every kind of scenario when dealing with unexpected input can be a bit much. There's actually a much simpler way of dealing with this in Python. Here, you'll learn how to handle errors with try and except blocks. First, let's learn more about what errors in Python are. We've seen error messages due to several reasons in this course, and we can separate them into two types: syntax errors and exceptions. Syntax errors occur when Python can't interpret our code, since we didn't follow the correct syntax for Python. These are errors you're likely to get when you make a typo or you're first starting to learn Python. Here, I get a syntax error because I missed the ending quotation mark at the end of the string. I can see this in the error message: syntax error, end of line when scanning string literal. The other kind of error, exceptions, occur when unexpected things happen during the execution of the code. Here, although our code is syntactically correct, we run into an exception because the string spelling out 10 isn't a valid argument for the int function. There are different types of built-in exceptions in Python, and you can see which exception is being thrown here in the error message. Value error is one type of exception. It occurs when a built-in operation or function is given an argument with the correct type, but an inappropriate value. Here's another example that throws an exception. Here, we try to reference a variable name that we didn't define yet, so we get a name error exception. Again, this code is syntactically correct, but when Python gets to this line of code, it can't find the value for this variable when it tries to run it, so it raises an exception and stops the code. In Python, there are ways to handle exceptions so they don't always crash our program when they occur. Let's look back at this example that takes in input from the user. We saw that when we ran this code, it got an error when the user inputs something that can't be converted to an int. We can actually handle this error using a try statement. In a try statement, the code inside the try block is first run, and if Python runs into any exceptions while it's running this block, it will jump to the code in the except block. Here, if I run this code and enter the word 10, it prints "that's not a valid number" and moves on to the rest of the code. The program continues to run whether or not it runs into an exception during this try block. For example, if I have a line after this try statement that prints attempted input, you'll see this is printed in both cases. If we want this code to keep running until the user inputs a valid number, we can use a while loop and break the loop if all the code in the try block successfully executes. Here, the program keeps taking in input until I enter a valid number. If I enter a valid number, this statement in the try block doesn't raise an exception, so it moves on to the next line, where it breaks from the loop. However, since it breaks from the loop, it never prints attempted input. If we want this last line to always run after the try statement no matter what, there is an optional component of the try statement we can use: finally. Now, attempted input will be printed when the program is exiting this try statement under any conditions, whether there's a break statement, return statement, or error that causes this program to crash within the except block. You can read more about this in the notes below. The finally block is useful for cleaning up actions in your code. Later in the lesson, we'll use this to close a file after attempting to open one in a try statement. Here, the code in the except block occurs when any kind of exception occurs while executing the try block. Really though, we just want to address the value error exception. If I try to exit the program with Ctrl+C, it doesn't stop the program because the except handles any error, including the keyboard interrupt error. We can actually specify which error we want to handle, like this. Now it catches the value error exception, but but not other exceptions like keyboard interrupt. Notice in this case, when I press Ctrl+C, it ends the program. This is because a keyboard interrupt exception was raised, which isn't handled by this try statement. Also notice that although the program crashed, this code in the finally block was still executed. Attempted input is printed no matter what, as the program is exiting this try statement, even if that means exiting the program. If we want this handler to address more than one type of exception, we can include a tuple after the except, with the exceptions like this. Or, if we want to execute different blocks of code, depending on the exception, you can have multiple except blocks like this. Here I have two handlers, one for value error and one for keyboard interrupt. When I press Ctrl+C, it says no input taken and breaks from the while loop. In order for a program to be really useful, it needs to interact with real-world data. Images, web pages, and databases are all examples of files, and we routinely create, move, manipulate, and read these files in our daily digital lives. All the data we've used so far has been defined inside the Python script or raw input from the user during execution of the script. Next, we're going to massively increase the variety of what we can achieve in our Python programming by introducing how to read and write files in Python. This will allow us to interact with and process larger amounts of information from many more sources. All kinds of files have a similar structure on a computer. There are strings of characters that encode some information. The specific file format, often indicated by the extension of the file name, such as .py, txt, htm, csv, and many more, will indicate how those characters are organized. The characters in a file are interpreted by the various programs we use to interact with them. For example, an image editing program will interpret the information of a digital photograph file and display the image. If we then edit the image in the program, we're using this program to make changes to the characters in the file. In Python, we can read those file characters directly. The experience will seem quite different from opening a file in a desktop application. Opening files in Python gives us a common programmatic interface to all kinds of files without the need for a graphical user interface, which means we can automate tasks involving files with Python programs. Let's see how we read information from a file into Python. To read from a file, we first need to open it, which we can accomplish with the built-in function open. We include a string with the path to the file, along with any optional parameters we want to specify. The open function returns a file object, which is a Python object through which Python interacts with the file itself. Here, we assign this file object to the variable f. This second optional parameter specifies the mode in which we open the file. In this case, R, or read only. We are using this mode since we only want to read from the file. We don't want to change any of its contents. This parameter isn't really necessary for us to include here though, since the mode defaults to read only if unspecified. Once we opened our file and created a file object, we can use the read method to access the contents of this file. This read method takes the text contained in a file and puts it into a string. Here, we assign the string returned from this method into the variable file data. When we are finished with the file f, we should close it. This will free up any system resources taken up by the file. Here's an example that uses this file, sumefile.txt. It's important to remember to always close files we have opened once we no longer need them. If we open a lot of files without closing them, we can run out of file handles, and we won't be able to open any new files. Exactly how many files you can open before running out of handles will depend on your operating system. To convince yourself, you can try running the following script in Python. At some point for a large enough number, you will receive an error. We can see that at 7,164 open files, the system no longer had available resources to open any new files. To avoid this, it is always a good idea to close any files you no longer need. Opening a file object is like opening a window to look into a file. To be more precise, it's a window that's only 1 character wide, and it always starts off at the very start of the file. This is very different from reading a book or a document where you can look at multiple words or even pages at once. Think instead of the file as a long stream of characters. The file object can look at just 1 character at a time in order. In addition to reading from a file, you can also write to a file, in which case you will change the content of the file. To do so, you must open the file in writing mode. Be careful once you open a file in writing mode. Anything that it contained previously will be deleted. If you're interested in adding to an existing file without deleting its content, you should use append instead of write. You can visit the Python documentation for more information on the different modes in which you can open a file. Since we're in write mode and I don't want to delete what's in this file, let's use another one. If the file does not exist, Python will create it for you. We can now write to the file like this. And after we're done, we will close it like good citizens. Here, you can see that Python created another file which contains the text "Hello World." It could be easy to forget to close a file when you're done using it, so Python provides a special syntax that auto-closes it. This with keyword allows you to open a file, do operations on it, and automatically close it after the indented code is executed, in this case, reading from the file. Now, we don't have to call f.close. This code, as f, assigns the file object created by the open function to the variable name f. This line of code is basically this line of code, except you can only access the file object f within this block. This is another kind of scope. Once you leave this indented block, the file is closed and you are no longer able to interact with it. For example, trying to call f.read outside this block like this would return an error. However, just because you closed the file doesn't mean you lose the data. Here, we read in the file in this line and get this file data string that has the text contained in the file. Calling file data outside the block works fine. We can use all the usual string methods on this file data string to process its contents. In addition to reading in data from files, we can actually import Python code from other scripts. This is especially helpful if you're working on a bigger project where you want to organize your code into multiple files and reuse code in those files. If the Python script you want to import is in the same directory as your current script, you just type import followed by the name of the file without the .py extension. Import statements are written at the top of a Python script, each one on a separate line. Python will still run if import statements are included later in the script, but it's common practice to always have these at the top. You're only able to access what you've imported after this statement, so it's just less confusing to have these written first. It's also nice for readers to see what a script depends on before reading the rest of the code. Let's start with a really simple example. Here, I have a Python file called otherscript.py that just prints 2 plus 3. And in this file, demo.py, I import other script and then print 4. When we run demo.py, this import statement tells Python to run code from that file, which prints 5. It then continues to execute the rest of the code in this file, printing 4. If instead this file had the line num equals 2 plus 3, and we tried to access this in demo.py, referencing it with just the name of the variable would return an error. To access objects in otherscript.py, we need to use the name of the file followed by a dot followed by the object to tell Python to look for this object in the other script file we imported. Now it accesses the variable successfully. When Python runs this script, it only has direct access to objects defined in this script. One of these objects is a module called otherscript. A module is just a file with Python definitions and statements. When we import a Python file like this, it creates an object called OtherScript with the type module. Let's see a more useful example of importing a module. Here, we have a Python file that contains useful functions we would like to use. One that returns the mean of a list, and one that adds 5 to each element of a list. We can import them into demo.py and type usefulfunctions.the name of the function to use them. You can imagine this would be very helpful if we had many functions used a lot in different files. Although it seems a little annoying that we have to type out the whole name of the file each time we want to use a function from it. We can make this much simpler by adding an alias. Here, I made an alias for the useful functions module, UF. Now, I can just type UF instead of the whole module name when calling functions from it. This is useful when we have objects we want to import from other Python scripts, like functions. But what if that script also includes executable statements in addition to function definitions that we don't want to import? For example, what if usefulfunctions.py has code at the bottom of the script that tests its functions and prints the results? This code is nice if we run usefulfunctions.py to test out these functions, but unnecessary if we're just trying to use these functions in another script. Here is where we can use this statement, if name equals main. By including these executable statements inside this if main block, we tell Python to execute this code only when the main program being executed is this usefulfunctions.py. If we run this file, the code inside this block is run. However, if we run another script that simply imports usefulfunction.py, this code is not run. Generally, it's good practice to write executable statements inside an if name block, or alternatively, include them in a function called main and call this in the if main block. You're probably wondering what this name and main stuff is. Whenever we run a script like this, Python actually sets a special built-in variable called name with 2 underscores before and after it for any module. Here, since we ran python demo.py, Python recognizes this module as the main program and sets the name variable for this module to the string main. For any modules that are imported in this script, this built-in name variable is just set to the name of that module. You've seen how helpful it could be to import your own modules. But what if I told you there was an entire library of built-in modules that just come with Python? This is the Python standard library. Up here, you see built-in objects we use throughout this course, like built-in functions, data types, and exceptions. Below that, though, are tons of useful modules that you can import. Think of this library as a very big set of tools that you can use to help you program in Python. It provides new types of objects and functions for a range of common and specialized tasks. Other people have already written this code and put it into useful modules for you to use. Using modules from the Python standard library to easily access and use existing code gives you a lot of programming power. The Python standard library is organized into modules. Many modules are simply Python files, like the Python scripts you've already written and imported. Let's import this math module. Again, an import statement runs the code in the module. Modules typically contain a lot of definitions and usually don't show any output. Running the code will make all the module's functions and types of objects available to use. Math has a factorial function, which finds the product of a number and all the positive integers less than it. 4 times 3 times 2 times 1 is 24, so math factorial 4 prints 24. The Python standard library has good documentation for each of its modules, and it's a good idea to read the relevant page whenever you use one. Here's the documentation for the math module. So far, you've seen only one module in the Python standard library. It's a good one, but there are many more. If you look at the documentation for the whole of the Python standard library, modules are listed in groups based on their uses. Clicking on a name takes you to the documentation for that module, which often includes example code that you should feel free to test out. So far, you've imported modules with import followed by the module name, which makes all of the classes of objects and functions of that module available via dot notation. There are some other variants of importing that are useful in other situations. You can import an individual function or class from a module like this. From the module name, import the object name. This gives access only to default dict from the collections module. Default dict will be accessible with its own name without the module name before it. Trying to access collections or even calling collections.defaultDict will give a name error. Importing individual objects from a module means you only take what you need and you don't need to use dot notation to access them. You can import multiple individual objects from a module by separating them with commas. This technique is very common when importing pieces from large libraries. And as you saw before, you can import a module and give it a different, usually shorter name like this. If the name of a module is particularly long, or if there's a clash with something with the same or similar name, renaming the module like this can be helpful. Check code examples in the documentation, as these will often include a standard abbreviation if one is used for this module. Using an abbreviation that is consistent with others will make your code more readable. For example, the standard abbreviation for the multiprocessing module is MP. You can combine the previous two pieces of syntax to import an item from a module and change its name. Again, you'll be able to access only that individual item directly with its newly specified name. No dot notation is needed. This can be useful if you have multiple objects with similar names from different packages in your namespace. For example, perhaps you want a CSV reader and a JSON reader. You could import them from their respective modules and give them descriptive names. Another way of importing that you may see in other people's code but that you should not use is this. Using this asterisk will import every object from a module individually and allow you to access each of them directly via its name. The real problem with this is that modules may contain many objects, each of which has a name. Including all of these names may overwrite or may be overwritten by other names you're using in your program. Import star also makes it impossible for collaborators to find where an imported object was defined. A reader can search for the definition of a function and not find it, and they won't know which import star statement introduced the function. These problems can lead to a lot of confusion. Do not use from module name import asterisk. If you really want to use all the objects from the random module, use the standard import random instead, and access each of the objects with the dot notation. Some of the modules in the Python standard library have a lot in them. In order to manage the code better, they are split down into submodules that are contained within a package. A package is simply a module that contains submodules. A submodule is specified with the usual dot notation. For example, the OS module, which is useful for dealing with file systems, has a submodule, os.path, which is used specifically for dealing with path names. Modules that are submodules are specified by the package name and then the submodule name separated by a dot. You can import the submodule os.path like this. You can then use the objects from the submodule in the usual way. However, this syntax for importing will only work for submodules. You cannot import a function from a module in this way. If you want to use other parts of the OS module too, you could import OS instead, and everything in the os.path will still be accessible. Sometimes, naming can be a point of confusion when working with modules. For example, a module might be named after one of the important classes or functions within it. In this case, you'll need to think carefully about your import statements. This imports the datetime class from the datetime module. Note that after this, using datetime will refer to the datetime class, not the module. Compared to most languages, Python has a large standard library. In fact, people say Python comes with batteries included because it comes with the libraries you need to get right to work. However, the standard library doesn't come with everything you might want. Some tasks are too specialized to be accommodated by the standard library. Fortunately, there are tens of thousands of third-party libraries written by independent developers. How do we get these packages, though, if they aren't included with Python itself? We can install libraries using pip, a package manager that is included with Python 3. Pip is the standard package manager for Python, but it isn't the only one. One popular alternative is Anaconda, which is designed specifically for data science. Here, we'll use pip, which is a general standard. Let's use pip to install this library, which is used for working with time zones, a remarkably complicated task. This command will download and install the package so that it's available to import in our programs. Once installed, we can import third-party packages using the same syntax we use to import from the standard library. In this example, I import the time zone package along with the date time from the standard library. It's standard practice to put the import statements for third-party libraries after imports from the standard library. This example stores the current time expressed in terms of Coordinated Universal Time, or UTC, in the variable now. It then translates this time into IST, Indian Standard Time, and stores that in the variable ISTNow. Larger Python programs might depend on dozens of third-party packages. To make it easier to share these programs, programmers often list a project's dependencies in a file called requirements.txt. This is an example of a requirements.txt file. Each line of the file includes the name of a package and its version number. The version number is technically optional, but it usually should be included. Libraries can change subtly or dramatically between versions, so it's important to use the same library versions that the program's author used when they wrote the program. You can use pip to install all of a project's dependencies at once with this command. If you open your terminal and type Python, you should see something like this. This is the Python Interactive Interpreter. You can type here to interact with Python directly. You just type your code, press enter, and the output will appear on the following line. This is a good place to experiment and try bits of Python code at a time. Notice here I didn't have to print the type to see the output. In the interpreter, the value of the last line in a prompt will be outputted automatically. If you had multiple lines where you'd want to output values, you'd still have to use print. If you start to define a function, you will see a change in the prompt to signify that this is a continuation line. You'll have to include your own indentation as you define the function. A drawback of the interpreter is that it's tricky to edit code. If you made a mistake when typing this function, or forgot to indent the body of the function, you can't use the mouse to click your cursor where you want it. You have to navigate with the arrow keys to move the cursor forwards and backwards to the line itself for editing. It will be helpful for you to learn useful shortcuts for actions like moving to the beginning or end of the line. Notice I can reference any objects I defined earlier in the interpreter. One useful trick is using the up and down arrow to cycle through your recent commands at the interactive prompt. This can be useful to rerun or adapt code you've already tried. To quit the Python Interactive Interpreter, use the command exit with parentheses, or hit Ctrl-D on Mac or Linux, or Ctrl-Z and Enter for Windows. There is actually a really good alternative to the default Python interpreter, IPython, which comes with many additional features, like tab completion, which completes words for you, or shows what options are available if there are multiple. This can be useful if you want to see what methods are available for an object. Another useful trick is this question mark to get details about a particular object. I can quickly see what this function does without looking up the documentation. You can also execute system shell commands using an exclamation point, and some common ones don't even require it. You can learn more about IPython in the notes below. Using an interpreter can be really helpful for experimenting and testing Python code. though it's not necessarily just for experimentation. I also use the interpreter when I want to quickly investigate or modify files using Python. Awesome job completing this course! After covering lessons on Python's data types and operators, control flow, functions, and scripting, you've developed the understanding and skills necessary to tackle projects and courses in Python. Congratulations again on completing this course. If you recall from the previous lesson, iterables are objects that can return one of its elements at a time. Lists are one of the most common iterables you have used. It turns out many of the built-in functions we've used so far, such as enumerate, return something called an iterator. An iterator is an object that represents a stream of data. This is different from a list, which is also an iterable, but not an iterator, since it is not a stream of data. Soon, you'll see some reasons that iterators are favored in different situations. Here, we will learn how to create iterators using generators. Generators are a simple way to create iterators using functions. However, it's not the only way to create iterators. You can read more about this in the notes below. These terms may be a little confusing. The term generator is often used to refer to the generator function, but it's also used to refer to the iterator object produced by the function. Here, I'll differentiate these by referring to the function as a generator function and what it produces as the iterator. Here is a generator function called myRange that produces a stream of numbers from 0 to x minus 1. Notice that instead of using the return keyword, this uses yield. This allows the function to return values one at a time and start where it left off each time it's called. This yield keyword is what differentiates a generator from a typical function. As you can see here, calling myRange4 returns an iterator that we can then iterate through. Using a for loop, we can print values from this stream of data. Here, this prints 0, 1, 2, and 3. In the next section, you'll get some practice writing generator functions to create your own iterators.